In this video, we're going to be looking at how we can use logarithms to help simplify certain functions before we differentiate them. To start off with, let's just remind ourselves about logarithms themselves. So, if we have y equals the log of x, then this means log to base e. And if we differentiate that, dy by dx is equal to 1 over x. But of course, inside this logarithm here, this might not just be x, it might be a function of x. So it might be y equals the log of a function of x. So what happens when we differentiate this? Well, we have a rule that tells us that dy by dx is equal to the derivative of f of x, that's f dashed x, over f of x. Now, we're going to be making use of these results, but also the properties of logarithms themselves. So, let's take our first example. Y equals the natural log of 3x to the fourth plus 7, all raised to the fifth power. And we want to be able to differentiate this. Well, it looks very complicated in here, but here we're raising 3x to the power 4 plus 7 to the power 5. And one of the things we do know about logarithms is that if we're raising what's inside the log to the power 5, that's exactly the same as multiplying the log by 5. So in other words, we can rewrite this as y equals 5 times the log of 3x to the 4 plus 7, using our laws of logarithms. And now this is now much easier to differentiate because this inside the log is a very straightforward function. So we can now differentiate dy by dx is equal to 5 times by. Now let's remember what we do. This is the function inside the log, so we differentiate that. So that gives us 12x cubed, and the derivative of the 7 is 0, over the function itself, 3x to the fourth plus 7. And if we just do a little bit of simplifying, 5 times by 12 gives us 60, x cubed over 3x to the fourth plus 7. And what looked like up here quite a fearsome derivative that we were going to have to do, here it's turned out quite simply. So let's have a look at another example. Supposing we've got y equals the log of, we've got 1 minus 3x divided by 1 plus 2x. Now, what we've got here is the log of a quotient. And there is a formula for differentiating a quotient. That's going to lead to a very, very complicated expression. But what we can do is make use of the laws of logarithms, because the laws of logarithms tell us that when we're doing the log of a quotient, then that is simply the log of the numerator minus the log of the denominator. Because in logarithms, we do division by subtracting the logs of the respective parts. And now these two are both very easy to differentiate. So we can have dy by dx equals, and this is a function of x, 1 minus 3x, so we differentiate it, that's minus 3 over the function itself, 1 minus 3x. Minus, that's that minus sign, and now we do the same for this logarithm. Here's the function of x which we differentiate, So the derivative of 1 plus 2x is 2 over the function itself, 1 plus 2x. Now, there is a penalty to pay for getting away with such a straightforward differentiation. What we have to do now is put these two together. We have to bring them together all over the same denominator. And this is our denominator, the product of these two. So that's 1 minus 3x times by 1 plus 2x. So we ask ourselves, how many times does this divide into this? And the answer is 1 plus 2x. So we have minus 3 times 1 plus 2x minus 2, and then how many times does this go into this? And the answer is 1 minus 3x, so it's 2 times 1 minus 3x. Now we need to simplify this, so we can keep the denominator as it is, 1 minus 3x times by 1 plus 2x. And let's multiply out this bracket. Minus 3 times everything inside the bracket. So it's minus 3 minus 6x. And then minus 2 times everything inside the bracket. So that's minus 2 plus 6x. Now we need to simplify this bit on top. And we've minus 6x plus 6x. So that's no x's. Minus 3 minus 2. So that's minus 5. So we have minus 5 over 1 minus 3x times by 1 plus 2x. But so long as we're good with the algebra, this differentiation is well worth the simplifying as we have done here. So let's take another example. This time, let's take y equals x to the power sine x. Now, real problems having the unknown, the variable, appear yet again in the power, in the index. So this sine x is the problem. If it wasn't in the index, we might be able to differentiate it. But one way of getting it down, so to speak, out of the index is to take logs of both sides. So we have log of y equals the log of x to the power sine x. And if we remember, by using our log laws, when we raise the function inside the log to a power, then that's just the same as multiplying the log of the function by the power. And now this is a straightforward product. It's sine x times by log x. And we know that we can differentiate this. What about this at the left-hand side, log y? Well, if we're differentiating with respect to x, we can differentiate this, log y, implicitly. And so the derivative of the log of y is 1 over y times dy by dx equals, now we need to differentiate this, sine x times by log x. It's a product, u times by v. And we know that the derivative of a product is u times dv by dx plus v times du by dx. So let's write that down. U, which we said was sine x, times dv by dx. And the derivative of log x is 1 over x. Plus v, which is log x, times the derivative of u. And u is sine x, its derivative is therefore cos x. Now, we can do a little bit of simplifying here. we can put it all over this denominator of x. And so we have sine x plus, and if we're putting everything over this denominator of x, we need to multiply anything that's not over the denominator of x already by x. So that's x times log x times cos x all over x. But at this side we've 1 over y, and what we're really after is dy by dx. And so we need to multiply up by y. But we know what y is. It's x to the power sine x. So that's sine x, x log x, cos x, all over x, and we're going to multiply up by y. And that's x sine x to the power sine x. And so we finished the differentiation. And again, something that looked impossible at the beginning, by making use of the laws of logs, we have been able to differentiate. So let's take a look at another example, this time a more complicated one, a quotient, one that really is quite complex. Now, again, we could do this as a quotient, u over v, and use the formula, which, if we remember, is v du by dx minus u dv by dx all over v squared. But simply having said it, that's quite frightening. So if we have a look at this, one of the ways we can do it is to take logs of both sides. And then, having taken logs of both sides, we can make use of our laws of logarithms to simplify this side. So let's begin by remembering that if we have a quotient, when we do the logarithm, then that's the log of the numerator minus the log of the denominator. But we can simplify this one even further, because we're raising 1 minus 2x to the power 3. And in terms of our laws of logs, that's exactly the same as multiplying the log of 1 minus 2x by 3. Minus, now here we've got a square root. And the square root is the same as raising something to the power a half. So that this is exactly the same as taking a half of the log of 1 plus x squared. And now what we see is that this that we've got here is much simpler to differentiate. So we can do that. The derivative of the log of y, doing it implicitly, is 1 over y dy by dx equals 3 times, now we want to now differentiate the log of 1 minus 2x, so the function is 1 minus 2x, so we differentiate that, that's minus 2 over 1 minus 2x, minus a half, differentiating the log of 1 plus x squared, the function is 1 plus x squared, so its derivative is 2x over 1 plus x squared. Again, there's a penalty to be paid. We really ought to put these back together again so it's all 1. So let's do that, and let's just simplify a little bit here. There's a 2, we'll cancel there with a 2. So we've got 1 over y dy by dx is equal to, we've got 3 times by minus 2 over 1 minus 2x. So that's going to give us minus 6 all over 1 minus 2x. We've got minus x over 1 plus x squared. And now we need to bring these two terms together. So we look for a common denominator, and that must be the product of the two denominators. And 1 minus 2x goes into this, 1 plus x squared times. That's minus 6 times by 1 plus x squared. Minus x times by, well, 1 plus x squared goes into the whole of this, 1 minus 2x times. So we need to multiply the minus x by 1 minus 2x. Multiply out the bracket. Minus 6 minus 6x squared minus x plus 2x squared all over 1 minus 2x, 1 plus x squared. We can simplify the top. Minus 6 minus x minus 4x squared all over 1 minus 2x, 1 plus x squared. And now, finally, we want dy by dx equals, well, it's going to be this. Let's take that minus sign out. So we have minus 6 plus x plus 4x squared all over 1 minus 2x times by 1 plus x squared. And we need to multiply both sides by y. And let's just recall what y was. Y was 1 minus 2x all cubed. So that's 1 minus 2x all cubed all over 1 plus x squared square root of. And clearly there's a little bit more simplify can be done here because we've got a 1 minus 2x here and a 1 minus 2x cubed there. So we can cancel that with one of those. Here we've got a 1 plus x squared times by the square root of 1 plus x squared. And if we follow our laws of indices, that's to the power 1, and this is to the power 1/2. And so if we add them together, that gives us to the power 3 over 2. So, dy by dx, finally, will be, let's take this top line, minus 6 plus x plus 4x squared times by 1 minus 2x squared, 1 minus 2x all squared, all over, and just check on that denominator, 1 plus x squared to the power 1 times by 1 plus x squared to the power 1/2. And the 1 and add it to the 1/2 gives us 1/2 or 3 over 2. So that's 1 plus x squared raised to the power 3 over 2. So what we've seen in this video is that we can use the laws of logarithms to help us simplify certain functions before we come to differentiating them. That can make the whole process of differentiation so much simpler.